Next in this session, we'll see the bitwise operator. Uh, sorry, exactly these are same as logical operators, but instead of doing the logical operations on a number as a whole, it will do bitwise logical operation. Yeah. So the operators remain same, and or we have new operators XOR. This is shifting operator, left shift and right shift. Yeah. So um, this will not produce either true or false result. This will produce a completely entirely a new number. Yeah. Say 10 and with 5, it will not produce 0 or 1, unlike it produced in the logical operation. So it will produce entirely a new number. So that we'll see how it produces a new number in the code. Yeah. So this is the code block, and I'll remove this code and then take some. For the ease, I'll use the hexadecimal number. Yeah. A and B is equal to 0x 01. Yeah. Or 0x 0f. And now C is equal to A and B. Yeah. It's just a single and here we're not doing the logical and. So if we print this, we will get a logical like each bit of the A will be converted, will be ANDed with each bit of B, and an entirely new number will be generated. A new number will be evaluated. Let's see what it produces as output. Yeah, here it has given me 14. Yeah. So let's print it in the hex format. So if I write X, it will print in hex format. So this is 0E. Yeah, 0E. That's because 0 here, all the bits will be 0. 0 and with anything is 0. And F is all ones. And E is all ones except the last bit. So that's why it has resulted into E. Yeah. I think it will, in the binary format, it looks like this. So this whole thing is 0. So if you AND each bit, I think the resultant would be this one. Yeah, only these 3 bits will be ones, and yeah, that's what we have here. I'll remove this, otherwise it will not compile. Or just add binary format of this is equal to 1111 1110. Same goes for this 000 1111. Yeah. So the binary AND, the bitwise AND, this is what the bitwise AND will do. Now if we OR, I think we'll get the FF as a value, because every bit will become 1, because some or the other way there is one bit is 1. Yeah. So if I compile it, let's compile and see. Yeah. So this is FF. That's because everything is turned into 1 now. All the bits are turned into 1. Let's see. Let's try to make it something else. Let's try 5 here, and 5 will be represented in binary as 0101. Yeah. So then the resultant would be only this bit 1, that is 5. 5F will be the result. Let's see if it is printing 5F. Yeah, it is printing 5F, what we calculated. So in this way, the bitwise logical operations are performed using these operators. We saw the bitwise AND and bitwise OR operators. Next we see what the XOR does. Uh, like you all know, XOR gate does not XOR operations. It's like 0 0 is 1, 1 0 is 0, 0 0 is again 1. So the same number produces 1. Yeah. Let's see if this is doing its job. Yeah, we have a result here, and that's 0x51. So here the 5 is coming, 0 1 0 1, so that is 5, and then next has to be 1. That's because all these 3 bits are 1, so it will all become 0, and 0 1 becomes 1. That's why 5 1. Yeah. So the XOR, this is how we do XOR. This is the XOR symbol. So, and this is how we print the hexadecimal number. So next one is the shifting operators. So shifting operator is a very important operator with respect to arithmetic as well. So you can ask how the shifting operators are related to the arithmetic operators. Yeah. So what we know from the maths or the from the binary representation of a number is this number. If this 1 comes here, yeah. So let's take an example of the binary. Let me just try to explaining the binary. So say we have a number 0 0 0 1. So this completely represents 1 as a whole. Yeah? So now if I shift this 1 here, then it will become like this. Shift by 1, it's like multiply by 2. Again, if you shift, this will become 4. Shift that by 1, it will become 8. So in a way, we are using the shift operator as a replacement for multiplication. And what is the advantage of this over multiplication is multiplication takes more number of instruction cycles in the execution. So the execution will be slow if you use a lot of multiplications. So wherever possible, if you can do that multiplication with shift, it will be better to do with shift to save a lot of time. I'll take one example. I will try to find the 2 to the power n using the shift operator. Let's see the basic shift function. So I take a equal to 0x4, yeah, and I will be shift a left shift it by 1. Yeah. So as we see, if we left shift it by 1, I'm expecting it to produce a result of 8. Yeah, so it is producing result of 8. So it has shifted the value. And next, same way, you can do the right shift. Right shift is divisible by 1, divisible by 2. So if I right shift it, then it should print me 2. Let's see if it does. It does print me 2. Yeah. So we'll quickly see if we have to find a square of a number, a 2 to the power n. Yeah, 2 to the power 20. Correct? In that case, how do we do? First, take an example, 2 to the power 4. 2 to the power 4 is 16. So 1 left shifted by 4. I'm expecting it to print 16 or 8. Let's see what it prints. Yeah, it is printing 0x10, that is 16 in the hexadecimal. Let's remove hex and do it in the decimal for ease. So it is printing 16. So this is my n, which is 4. I wanted to calculate 2 to the power 4. And now see if I have to calculate 2 to the power 32, you just have to write 32 here and then build it. Yes, integer cannot represent a value 2 to the power 32. Yeah, and it has done the rollover. We saw that the one left shifted by 32 is giving a overflow value. So what I'll do, I'll take C and I'll do 1 left shifted by 31. Yeah. So we'll use U now. I'll tell you the reason. Let's print it and see what does it print. It's printing this value. Just to be confirm that what it has done, let's print the hexadecimal value. So it has printed this much, yeah, 8000. So what you see here, 8, yeah. So and we'll see in the subsequent chapters the significance of the signed bit. Yeah, we say signed integer, but to computer we can only represent anything in 0 or 1. So signed and unsigned are represented as bits. Okay, let's see what happens, what data it will print if I use minus %d. So it's printing a negative value. That's because the d is used to represent a signed integer. The moment we do it shift by 31, the MSB of the number becomes 1, and that's actually a signed bit. And if that becomes 1, it's printing it everything as 0, everything as negative. Yeah. So that's why we used U for representing the unsigned integer. Let's make 32. It will anyway print the 0 that we already know because of the rollover. Let's do -1. Yeah, -1, and let me print, use X here. This is to indicate, to see what it's printing. If you see, it's printing all F's. So this is 4 bytes, 1 byte, 2 byte, 3 and 4. Yeah, so all F's, so it cannot go beyond this. Yeah, let's see another example. How can we use shifting operators for the mathematical operations? Yeah, so here I want to demonstrate one use case of the shifting operator, that the intention is to calculate 2 to the power n. Yeah, we'll accept n from the computer input from the keyboard, and we print the 2 to the power n in the exponent. For example, 2 to the power 5 is equal to 32. So 32 will be printed in exponent. So the ideal way, without using the shifting operator, is to multiply to n times, yeah, in a for loop. So if we multiply to n times in for loop, that's also possible, but there will end up consuming a lot of instruction cycles, and that's not an efficient coding. So if when we have this option available using shifting operator, we can do that. Okay. First, accept the input. I'll accept the unsigned int, and this is how we accept. This is the ampersand. This is the ampersand sign, and here I'll accept, pass the address of n. Now we'll see how to calculate the exponent. It's a very simple step. 1 left shifted by n. I think this one instruction alone will give you 2 to the power n. Yeah, we'll see otherwise how much time it will take. Value of exponent. Let's take the unsigned int. Let's try printing it. Yeah. So when we are waiting for the input, let's give input here. Phi. What you're seeing, value of exponent is 32. Correct? Execute again. This time let's give another number. 10,024. Yeah. Because it's just shifting. There is just one instruction. Correct? So let's give 24. It's such a big number. It just did it in one instruction. I multiplied it 2 31 times or 24 times, just a very small fraction of a second. Otherwise, how it will be done is, if I don't have this, then I'll be forced to use a for loop for n equal to 0. Sorry, I have to use another variable. Let's take a standard I variable. I equal to 0, I less than n, I plus plus, and you have to multiply inside this, yeah, exponent equal to every time we have to multiply by 2 to the exponent. 2 into exponent. Two into exponent. Let's see what does it print. I plus plus here, there is a mistake. So if I give pi, so you're seeing 32. So what we saw is the conventional way, but when we have the option to do it using the shifting operators, it's better to do using shifting operator.